Another graph physics video presentation. So no reasonable comments, even by a broad definition to respond to. So we'll do a subject today, polarization. I've talked a little bit about the new theory of it and have advanced it another step forward. So I shall explain some of that. Maybe I have some crude notes here. Pop them up. I don't know how useful they'll be to you, but you can peruse them if you wish. So, yes, the theory is that when rays of light are created, not waves, okay, rays of light, that they travel through space as quanta, as, what you understand to be the magnetic and electric components, flying through space. That's not entirely sufficient. It's always something. All right, we'll turn on the other light. Excuse me for a moment. Okay, I'm back. You can see the little fish there. That's just a piece of one of your waves. Okay, your wave going this way and your wave going that way nonsense. Okay, magnetic and electric. Well, the real game is there's these little bits, and what they're out of is a slight out of alignment, and they can obviously be out of alignment in and out of the blackboard or up and down, and that is the polarization. And the polarization does, by let's call it all kind of coincidence, but it's really not a coincidence, that this polarization is proportional to the frequency, the distance of the frequency. So often, what is called the polarization, the depth of the polarization, would be the same thing as the wavelength. So that's the basic point, and as I've pointed out, this theory sort of fits with what we know about some things, like how human beings receive light in their eye. They need 6 of these things to get to their eye before we can say it's a photon, and other organisms can see photons we can't see because they only need 4 of these things with the proper period for their machine, their mechanism, to say, I see it, it's a photon, something happened. So anyway, let's go the step further in understanding how is this thing created. So the simplest way to understand it is with an antenna, and that you're basically just pump an electric current into the antenna, and the antenna produces the photons at this proper frequency. And so its frequency in, okay, is frequency out, essentially. So you're sending a pulse, essentially, of electricity. Now the pulse of electricity has a size. It's a it's on and off, but it's on a certain amount of time, and then it's off a certain amount of time, and then it's, if you're going to draw it, it would have some thickness to it, and then some thickness to it, and that's what you're sending. You're sending a signal that isn't happening in one instant of time. It takes time to send the volume of the signal. So if you want a lot of photons to come out, you have to send a lot of energy in, and the restrictions on that are the capacity of your conductor to pump the little bits of information, or the volume of information. So if you make this pulse too quick, if you make it a really quick pulse, obviously it can't hold as much stuff. And if you try to make it with a high voltage and high amperages, you're putting in more volume and trying to quicken how fast you put it in, that gets complicated in terms of now your wires are going to have a little bit of trouble pumping the information. But at any rate, there's an idea that you could understand that frequencies have huge differences. So when you go from like light to radio, you're talking about a length difference in terms of this frequency that is insanely gigantic. All right, you're talking about miles to nanometers. So I can't draw the proportions, but it's like the size of the United States versus, a fire hydrant. You know, gigantic difference. And so obviously your pulses, when you're sending these radio waves, you can send really long ones, really big clumps of on and off. And obviously when you're sending photons, you got to send little tiny clumps. They can't, tiny by comparison. So the size, the volume, the time, the length of time that you can be sending information, that is the length of time your clump takes to move across a space, is giant when you're sending radio waves, and it's tiny when you're sending photons. So just understand that there's a size, amount of time. So the key thing is that when the electricity is going in, what it's going to do, I think you can see that. I could just do a redraw. Just clean it up a little. You got all that, right? You got all that. Maybe in the future I'll have an advanced production studio. Yeah, I'll have like some kind of, slaves that'll, clean the blackboards for me and provide them to me, all nice and clean to draw on. Or I'll have a computer system that just does it for me, or whatever. So anyway, so let's put the antenna back in the picture. That's a crappy antenna. I mean, that just sucks. Yeah. Don't use that antenna. Nothing good will happen. Alright, we can put it right over here. So you have this idea of the antenna, this thing you're sticking up in the air, and then you're pumping electricity into it. And it's going to be pulsed. A certain size of a pulse you're going to put in there where you're saying, send energy, send energy, send energy, send energy. And it's going to take you time to say the words, send energy. And the amount of time it takes will tell you how big this thing is. And the idea, the simple idea is that energy has to go into the antenna, and what's going to happen is some of it's going to pop out of the antenna right there, and some of it, the amount of time it takes for the pulse, will be able to go all the way over here before it comes out. So what's dictating how big the polarization is, that how many atoms you've involved in it, is essentially decided by how big this pulse is, how long it lasts. So if you can make the pulse shorter and stronger, like shape it a little bit, you can cut this down a little bit, this polarization. You can make it less polarized, less sloppy. So the word for polarization in a sense is a kind of sloppiness. We're talking about stuff out of phase with each other, not out of phase, sorry, out of straight. It's not a straight line it's traveling. So I'll get to how that's important with filters in a moment. So anyway, the thing to understand is how it's created. So the average atom, as I understand it, is 0.5 nanometers. So you can sort of just do the math. If the average piece of light was 500, let's say, and so you can just do the simple math and come up with 1,000 nanometers, and or essentially, 1,000 atoms. So what you're basically saying is the electricity can travel at a certain speed, very fast, and that it can cover, in terms of the greatest distance away before it goes out and the shortest distance before it goes out, is going to cover 1,000 atoms. Okay, so basically you have that much of a difference between where the signal's coming from. So where this one and this one could be this difference of like 1,000 atoms. More importantly, we have this number nanometers. So the relationship's pretty close in terms of how many atoms it can cover. And the real thing that's deciding is what's the speed of this conductor, the antenna. So the antenna can slow it down just a little bit, and that's why it cuts it down to, say, 700, for the polarization. So they've never measured those things exactly. So when they say the polarization is proportional to the wavelength, it's not exactly the wavelength. So but you can see how it would be close, just based on the average size of an atom. All right, so that's how it's being emitted. And so obviously the antenna will have something to do with how much polarization you have in different directions, is how the energy gets through the device producing the photon. So in traditional radio antennas, you put the energy in one end, okay, and that's it. And it's basically the energy's seeking ground is essentially the reason why it goes up the antenna. And so if it was if you're talking about like a radar signal, a higher frequency but still radio waves, it'll only get 3 centimeters up the antenna. And so you don't need all this extra antenna, because it's really not going to do you any good, because your pulses can't really get any higher up the antenna. But if you're going with a lower frequency, well, then it has more time, and so now it can use more antenna. It'll also create more polarization, in the sense the difference between the photons will be much greater. And you'll also have the same problem then receiving. You'll need to receive, okay, with that same kind of length, because the photons were created moving, in different places in space, and you need to capture that. But the advantage of the antenna is that it'll create the polarization, generally speaking, in the direction of the antenna. So if you orient your antenna the same orientation as the other antenna, you're likely to pick up most of the signal, because most of it came from being polarized in one direction, the direction of the antenna. It has some polarization this way because it's a surface, and so the trick might be is if you make your antenna square instead of round, okay, you could theoretically, okay, create a better signal in certain directions. So if you wanted to go to New York City and, say, Philadelphia, you could model your antenna so it's shaped so it's likely to create photons in those directions. But anyway, you don't need to go into all that. All right, so next step is maybe filters. I don't know if we're ready for that yet. Well, why not? So the idea is just the frequency is going to dictate how far in the time a pulse takes to happen, how far up the antenna it goes. So you can modify, like say if you have radar, you could try to modify your radar by making your frequency, the length of your pulse as small as possible, and make your antenna even shorter, okay, and perhaps create a less polarized, less sloppy rays. And the less sloppy they are, the more information you can glean out of them in terms of detail. So, by modifying your signal going in, you can modify how much polarization comes out to some extent, theoretically. And I'm sure they take advantage of that. So, I'm not sure. I have some level of confidence that they do take advantage of that. So, anyway, all right. So the next part of understanding it is, so now if you understand that the polarization is really an out of alignment, the frequency is correct. Okay, so the wavelength is not disturbed. You're producing photons from the antenna, and they can be in certain polarization. And so it's really not a one atom phenomenon. So that's one of the conclusions I came to, is that even light polarization would be much wider than one atom. So one atom can't be receiving the whole photon, that it has to be something that more than one atom is doing. And that would make sense in the sense that the conductors happen to be the things that are good at receiving it, things with crystals. So things that have a matrix of atoms that are intimately connected to each other, and therefore share the same pressure, and therefore will react to a little bit coming in exactly the same way, because they share a common status, a common irritability, or whatever you want to call it. And so that's what makes them behave as if they're one atom. Alright, I don't know if you need all that detail either, but regardless. So a polarizing filter has this stuff coming at it that can be, depending on the antenna. Well, the other thing important to mention about antennas is when photons are created, we usually create them through some mechanism that creates them in a circular polarization, in the sense that they actually are polarized in both directions. They can have sloppiness in this direction, this direction. The ray can be fat in all directions. So if you were to look at the ray as it was leaving you, you can understand that a bit might be over there, and a bit might be over here, and a bit might be here, and a bit might be here, but it would be something in some sort of radius, okay, that represents close proportional to the frequency. The whole diameter would be proportional to the wavelength. And so there's stuff in that cone, that tube, essentially, of the ray. The ray is fat or thin. And so, depending on the source, like say, you could understand a light emitting diode, for example, is going to produce the light by a method. I mean, I won't get into all the physics of the structure, but the idea is that it's a flat plate, and what you're doing really is you're putting the electricity in the back side, and it's going through to the front surface. And so in a sense, you're going to create your photons in these places that are sort of consistent, in the sense of the emission will create a somewhat parallel, more parallel agitation of the surface. So you're not pumping it in and waiting for the electricity to go this way. You're really measuring how long does it take for a bit of your energy that you pump in to the back plate to get to the surface. And some of it gets to the surface in a straight line, and some of it doesn't get to the surface in a straight line. And that's really now what's part of your the idea of when the stuff went in is always going to be the same. And so all you're really saying is what part of the plate created the photon, and how did this ray go. That's probably the better way to draw it. All right. So you're talking about electricity going through the surface, and it's going to go in, and it can go to any one of these surfaces in the amount of time allowed. You see, it can't travel this far and have any hope of still being on phase, but it can travel this distance, or this distance, or this distance, or this distance, and excite an atom here, 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 or here. So the polarization will be within this range of out of alignment. Okay, so anyway, don't need that many details still. Alright, so what's happening when something's getting filtered by a surface or by going through something, reflecting? You can polarize light in the sense that you can screen it for defects, for certain defects. You can screen it for having something moving this way, or you can screen it for having stuff out of alignment this way. And by screen, that means you can interrupt the polarization. You can interrupt the phase, and therefore make the photon unreceivable. The photon still exists, you've just sort of broken an element of it, and you can put it back again. So I have explained this, that the polarizing filter, the kind that transmits light, not that reflects light, the reflecting one's a little more complicated, but it just has to do with the same principle. And the principle is you have a filter, a piece of plastic, it doesn't really matter, and what you're doing is you say you have a film here and a film here, and then you have twice as much film here and twice as much here. So you have two layers and you have one layer, and each layer creates a phase shift. So that means that if the photon's coming in, what it's going to do is retard it. It's going to create it so the photon takes extra time to get through, and so the photon will end up coming out here, or here, or here. So it's just retarding its progress. So it went into the filter and it just sort of got slowed down in time and space, and now it's behind. Okay, but it still has the same wavelength, and so everything else is still the same because it's slowing it down the same amount. Well, the trick is the stuff that might go through this filter. So if I have the light and it has this wide a polarization, you can see that maybe one element will get hit this thing over here, and the other elements will all go through this side. And so one element of the photon, if you had 4 bits to it, one of the elements isn't in the right position. It's over here now because it went through the slow filter. Okay, it was over here. Like say if it was polarized, there was stuff moving in all these directions, and it hit the film over here, and so this little bit here went through the double X one. It went through this filter, so it got twice as phase shift, and so now it's in the wrong position. And now this frequency is twice the frequency it should be, and so now this can't be received as a photon by your eye because it doesn't have the required number of bits in the required number of time. It's lost its frequency. And so technically if I ran the same photon through the filter again, okay, but this time these 3 bits go through the 2x and this one only goes through the 1x, well then this bit will be back in the right position, and now you'll see it as a photon. And that's exactly how polarizing filters work, in the sense that you can block all the light with 2 filters. All right, this one's killing the stuff out of alignment this way, one filter, and then the other filter is killing stuff out of alignment this way, and you wipe out every bit of all the photons. But then I can put one in at a 45-degree angle and restore it. And what I'm doing by putting that other filter in is I'm putting some of these back in before it goes into the next filter. So I've restored the 50% that was killed here. I put back 25% or 20% that are now photons again. And so this one's only going to kill 50% of that 70%. So I'm going to get my 20% out, or 30%, or whatever the numbers are. And so you're restoring the phase. Now the other evidence for this is that if anybody's worked with polarized light, these filters don't melt. So people have this idea, I had the idea, that the filter is killing the photon, that it's hitting something and it's blocking it, stopping it. Okay, and so it's essentially consuming a bunch of energy, but it doesn't get hot. And so that's clear evidence that this film is transparent, that the photons are going through both parts of the filter. It's just they're going through in a way that changes the the phase of the photon. So all the filter is doing is creating a phase shift, and you can undo the phase shift to some extent, to some degree. I mean, obviously there's you're going to break some of the ones that are okay. There's lots of places to have errors in trying to make a perfect filter where you take back what you took, but you're not going to be able to do that perfectly. So once you start messing these photons phases up, you can end up with all kinds of phase shifts where you'll never be able to restore the original wavelength. So is there anything else that needs to be said? So summarizing, we'll read some of the crap maybe, just so now you should be able to understand it better, the notes. All right, so visible light and radio is essentially, they really are the same thing. They're more similar than I thought they were, and because it really is just about how big the pulses are, and the pulses get smaller as the wavelength gets smaller. They have to. The duration, how long you pulse the energy, has to decrease. And the problem, like with radio waves, So you get them to go any distance, you have to pump a ton of photons in. So you can't make their pulse tiny because they won't have any, it's not enough photons. The light won't travel to New York City. So if you have an antenna 70 miles from New York City and you want to get the signal to New York, it's like a light bulb. You have to really pump a lot of light in to have any hope that any photons are going to get that far. Alright, bits of force traveling separated but on parallel paths. So the idea to understand is they are parallel. The photons are being pushed out and they're running a parallel course, essentially parallel. Obviously it does spread over distance to some extent, and you can receive the signal in different locations, and with radio waves you can also bounce them off of surfaces, so you can get the light to different places through something other than a straight path. But fundamentally they're traveling, the rays are traveling somewhat parallel. They do spread. We haven't been able to make a device that is so perfect where the surface is so, the atoms are so perfectly aligned with each other that they create a photon that every single bit of energy is traveling a perfectly parallel path. It's hard to manufacture that. Alright, so elements of ray can be selectively phase changed. So the bits can be changed in how fast they go through a surface, and by changing how fast they go through, you break their phase. And that phase can be restored just by slowing down the other bits, or it's pretty hard to speed up a photon bit, so you're kind of out of luck in terms of restoring it by speeding up the photon. There's no surface you can put it through to speed it up, so you're stuck with slowing down the others. Let's see. Okay, energy of the photons is not absorbed by the filter material, indicating it's not really destroying or blocking. So there's nothing really destructive happening to the bits. Most of them are going through. Obviously the material itself has some some opaquency. It's not perfectly transparent, so some of the photons are destroyed just as they are destroyed going through any material that seems transparent. Nothing's perfectly transparent as far as I know. Alright, so filter material, okay, nothing's blocked. Energy absorbed, transmitted, converted by a single atom. And I put a question mark. So it's obviously not a single atom, because the separation, the polarization, is bigger than a single atom. And that's why you need materials where the atoms are intimately connected, where they are fundamentally of a sameness, and that's why they conduct. They're conductors because they're connected, so anything that happens to one, the signal goes to the others really fast, and that's the nature of a conductor. So you give one pressure, another one can release it. So you can put energy into one atom, and 4 atoms away is where the energy will be released to the atmosphere. And that's sort of the nature of a conductor. So source has more time to spread from what position it creates elements of ray. So that's just about the energy goes in, and it's really a time equation. So the length of the pulse is going to tell you how far it can travel through the mechanism that's going to release the photons. And as I had in that one illustration, you can just kind of visually understand that if the pulse is, small, it can't get very far into the antenna, and that's why it wouldn't do you any good to have a taller antenna for transmitting, because the pulse doesn't have enough time to get all the way through the antenna and create photons at all the locations on the antenna. Okay, polarization, low frequency sources. So essentially the antenna becomes so much more important the bigger, the longer the chunk size of the pulse. The bigger that pulse, the more the antenna is going to obligate it to have a polarization. So I would argue that light is truly circularly polarized. The photons coming from the sun actually are not just in one arrangement, but in some of them are thick, they're big circumference. But it's also how they're created. So you have to sort of understand that the electricity that created them, the energy, was moving in a path. And so it went from this atom, this atom, this atom, this atom. There was a row of atoms that creates the photon. So that row would be a polarization. So it wouldn't be polarized in both dimensions, left, right, and up and down. It would only be polarized in the dimension that the pressure moved in. And obviously conductors do have that nature where the crystals would obligate the path to be in one direction. So light can be either polarized in one ray of light, can be either polarized in both directions, which is probably rare, or it can be it's polarized in one particular alignment, depending on the alignment of the crystals that are producing it. So you can sort of understand the crystals in the sun would probably be all over the place. So every photon is going to come out at it with a different alignment. All right. Right. So how far the electricity can travel in the time of the period. So that's the part about how far it can get into the antenna. And the shortest distance and the longest distance in that amount of time, how far you can get, that will be the polarization. The shortest distance to the outside world versus the longest in the amount of time of the pulse is essentially telling you how much the polarization will be. So I think that's enough. So I think it's a rational version of polarization versus all the other irrational ones. So I think I've never heard myself a rational explanation of polarization. I mean, something that makes any kind of sense at all. So this does. That's all I can say. So to me, it has to win because it's the only one that sounds like it's even close to a truth. So till the next time and such.